Okay, so in that last segment, we talked a lot about so qualitatively what's happening. Is a reaction spontaneous or non-spontaneous? And so in this section, we're going to go through and make this all a little bit more quantitative. We're actually going to put specific numbers on enthalpies, entropies, and free energy. The goals of this segment are to calculate entropies of reaction from standard state entropies, to calculate Gibbs free energies of reaction from standard state Gibbs free energies, and to calculate Gibbs free energies of reaction from standard state entropies and enthalpies, and to calculating the temperature when reactions become spontaneous. So we can tabulate standard molar enthalpies because entropy, like enthalpy, is a state function. All it depends on is the number of available states, right? It doesn't matter how it got there. So here are, is a tabulation of standard molar enthalpies for some common substances. And there's a lot of patterns you can notice. For example, if we compare the solids to the liquids, to the gases, you can see that gases are generally have higher entropy, which makes sense, right? They've got so many different ways to move around. More complex molecules, right, like calcium carbonate, iron oxide, you've got 5 atoms versus say iron, which only has 1. They've got more electrons. There's entropy associated with the electrons as well. We talked about it in the previous problem as just the sort of positions of the molecules, but it turns out there's entropy associated with the electrons as well. All the electrons moving around in the different orbitals. So more complex molecules have higher entropy, and then gases have higher entropy than liquids, which have higher entropy than solids. I mean, for very complex liquids, something like ethanol, you start getting up to being, around near the entropy of simple gases. But generally, it's things go pretty much in order. And then since the state function, you can calculate the change in entropy of the reaction simply by looking at the summing up the standard state entropy of the products and subtracting the standard state entropy of the reactant. So exactly the same as Hess's law. Okay. And again, all are the same temperature and pressure, 1 atmosphere. Technically, it's 1 bar now, but it's nearly the same as 1 atmosphere. You'll see them tabulated in both those ways, but the numbers are almost exactly the same because a bar is only like 1% difference than an atmosphere, and at 25 degrees C. So adding standard molar entropies, the entropy of reaction can be analyzed like the enthalpies of reactions. Like you said, that the total entropy of the reaction is simply the sum of the entropy of the products minus the sum of the entropy of the reactants. And one difference here is that elements in their pure state at 25 degrees C have entropy because of the entropy of both the electrons and the nuclei. So you don't have to set references for the enthalpy. Remember, because there is a reference for the entropy, which is everything being at absolute 0. And so you can use that reference. It turns out that's not an incredibly convenient reference to use. Instead, the reference that we generally use, because you can't actually calculate those. But what you can do is calculate as a reference instead H+, 1 proton, no electrons. So that's the simplest thing you can get to and that you can measure easily. And so that is used as the reference for these tables, 1 proton, no electrons. And so, for example, the entropy of iron is 27.3 joules per mole Kelvin, even though that's the most stable form of iron at room temperature. The entropy of H2 is actually 130.6 joules per mole Kelvin because it's a gas. So these are not 0 entropies. Okay, so what we do, how do we go through and calculate this? Well, let's just practice. So what's the entropy of the reaction? Calcium carbonate breaks apart into calcium oxide plus CO2 at 1 atmosphere and 25 degrees C. 1 atmosphere, 25 degrees C. We don't have to worry about like heat capacity, heating anything up. We can just say it's going to be standard state entropies and enthalpies. So our delta S of reaction is going to be the entropy of what's one product, CO2, plus one product, CaO, minus the entropy of CaCO3. And we can look these up from standard tables. I don't have them right here, but you can look it up. 213.6 joules per mole Kelvin. Makes sense, pretty big, it's a gas. The entropy of calcium oxide is 39.7 joules per mole Kelvin. Makes sense. It's not a gas. It should be much lower. Minus the entropy, 92.9 joules per mole Kelvin. It's a more complex solid, so it should have a larger entropy than CaO. And that ends up adding to 160.4 joules per mole Kelvin, which makes sense. It should be greater than 0 because we're going from no moles of gas to 1 moles of gas. So it's actually quite a large amount of entropy produced. So this makes sense from the qualitative analysis we did before.